If I can ask all of you just to mute your line while our speakers are speaking, just out of respect, so that they can present clearly and cleanly. And if you have any questions or comments or technical issues, you can use the chat. So I'll be monitoring the chat, and we can get back to you there. We'll leave the questions till the end, if you don't mind, and then we'll answer and address questions and discussion items at the end of the presentation, at which time you can feel free to put those in the chat, and I can read them out if you're not able to, or I'll put up your hand or put the question in the chat as well, and I can come on and get you to ask your question in person. So without any further ado, I'll introduce our speakers. We're hearing from Mike Watton and Shailene Haynes today. Mike is a research scientist with the Canadian Forest Service. His research has focused on linkages between fire weather, fuel moisture, and fire behavior, and he currently coordinates the research program to update the Canadian Forest Fire Danger Rating System. Shailene Haynes is a physical scientist with the Canadian Forest Service at the Great Lakes Forestry Centre in Sault Ste. Marie, Ontario, and also a PhD candidate at the University of Toronto. Her PhD research is focused on improving our understanding of drought in fire danger rating through field studies and remote sensing applications. And Shailene is a member also of the Canadian Forest Service Fire Danger Group. So with that, I'll turn it over to you if you're ready to go, Mike and Shailene.
Awesome. Thanks, Greg. And Shailene, I will just get you to drive this for the little bit that I'm talking, yeah, we'll get straight into things. Thanks, Greg. Thanks, Maria, actually, for letting us give another update here on pieces that are going on in the danger rating system. Jump forward here, Shailene. I like to start these out. A number of you will have seen this. A number of you will be bored from here with hearing me speak. I can tell you or promise you that I'm going to be quite short today, actually. What I like to do is start these out. Often I'm giving these update presentations overall, and just because I'm coordinating all this, have my hands in a lot of things, and sort of constantly keep the big picture in my head. And I want to make sure that as we develop this, we're consistently communicating to you out there in the fire management community. So, but I do like to show, it is a larger group. Here are some of the core folks who are involved from across the country within, in our Canadian Forest Service Fire Danger Rating Group. There's some, and there's, other folks who are contributing from outside of this list as well. Jump forward again, Shailene. Awesome. So for those of you who are unaware, maybe there's still folks out there. I mean, we've given a couple of these on this National Conversation Forum, but we are in the process of updating the danger rating system. I'll talk a bit more about that next, but we do have, last year we did put out an information report that gives you some of the rationale, some of the high level details about what the updates are going to entail. So I throw you these links here. You can download this from the Canadian Forest Service online publications site, and it's a good overview of this whole of the process that's going on. It doesn't get into the details of exactly what those changes are going to be, except at a very high level. Next one, Shailene. So we've been thinking about the elements of the next generation of the system probably for more than a decade now. I think if you think back 2 slides to that list that we had up there, only Steve and I have been around, and we're in this general working group that long. Steve Taylor, and Steve is far much older than I am, but we've been thinking about this for a while. We recently did accelerate the program and are trying to have something documented as the next generation of the system for around 2025. And the thing is, this isn't a complete tear down and rebuild of the danger rating system. The system has been evolving through the history of fire research in Canada, essentially. And we often talk about this current system that you all are using as being maybe around the 5th generation of the system. So we're just talking about an evolutionary step. Development will continue on after that point as well, that this generation, this next generation is finished off. There will be pieces in there that or there will be pieces missing from that some users will have been looking for. And our hope is, as it's, the research program focused on danger rating and physical fire science within the CFS has been going on since the 1930s, and we anticipate that continuing on. And that's an important one that I hope everybody recognizes. Next one, Shalene. And so we've been given these updates for a while, and one of the things that again, we're still in the process of working on models, and we spend a lot of time making sure that the system hangs together in a physically logical way and doesn't produce weird predictions when you drive it out to any of the extremes in terms of the input. So we've been, and that's completing that testing and even the implementation, the development of some of the models, is a couple of years off. But because it is a system that is integrated into a lot of your operational, decision-making information tools, we've been trying to give updates along the way. As I've been doing this, and we've done a few of these CFFC national conversations, and we focused as well on talking to individual agencies, sometimes in small groups, just to get discussions going. These discussions have been really useful, helped us realize a few things we're going to have to be, cognizant of as we move forward with the elements of the new system. So these discussions that come after a presentation like this, and certainly after the small group things that we've been doing in agencies, have been great. The problem is that is it's hard to get to everybody. These conversations are great, but there are a lot of things that are being updated, a lot of moving pieces. And so what we've done just recently is record some of these updates. And these are just informal recordings, mostly informal recordings of some of these presentations that we've given elsewhere, not dragging the presentation out, but re-recording them just so we're not stealing anybody's a webinar on your own site here. And so what we've done is put a few of these general introductions to some of the changes that are going to be happening in the danger rating system on collected them up on a YouTube site. And so if you go onto YouTube and search CFFDRS updates, there's a channel there, and it has a few of these update presentations that we've given to agencies just to give a bit of background on some of the things we're thinking about. Again, not final, it's not highly produced sort of stuff. It's just informal updates. So in case you haven't seen some of the more technical or some of the more detailed pieces that we're thinking about for, say, the FBP system or the FWI system. So I just wanted to point you at that. And next slide, Shalene, because today what we're going to do, because this update could take up the full hour, and I promised Shalene I would not take up any more time than I already have. What we decided we would do is point you at those updates on various things. For those of you who haven't seen me talk about some of the changes to the FWI system, I really have a look at some of those, small but important. But what we're going to do is focus on a piece of the new fuel moisture system, and it's a piece that Shalene has spent a lot of time over the last couple of years working on. And so I'm gonna just throw things over to you, Shalene.
Great, thanks very much, Mike. And thanks for the introduction, Greg. So as Mike mentioned, I'm just going to focus on a piece that relates to the fuel moisture system. And so this piece is largely revolves around drought, which, as Greg mentioned, is part of my PhD thesis. So we thought that drought it was a good timing to present some of this work, because some of you may be thinking about how to overwinter and what role drought plays in the spring fire season. So this work is, as I mentioned, part of my PhD thesis with my supervisors, Mike Watton and co-supervisor Mike Flanagan, as well as my committee members, Doug Wolford and Dave Martell. And then we have collaboration from a number of folks in the agencies and other partners. So I'll just get right into it here. Oh, and my keyboard's being weird. So just, to reiterate a couple of things that Mike mentioned that I like to think about, especially while I'm doing some of this this work that relates to the next generation, is, the Canadian Forest Fire Danger Rating System is the cornerstone of contemporary fire management across Canada. It's used day to day for a lot of decision making. And I think that stems from the fact that the models and indices that are part of the system are conceptually robust. So they give people answers along the lines of what they're thinking should happen. But as we know, there are some limitations, and that some of these limitations require greater interpretation by folks. So also we know that in the last few decades, new fire science data has become available, as well as new analysis capabilities and technology that allow us to advance the system to improve accuracy and to reduce some of the known biases. So, as Mike mentioned, this isn't a new overhaul. It isn't a complete overhaul. It is an opportunity to introduce some of these new technology and new advances into the system. And so one of the guiding principles that I like to remember is that, we intend to try and keep things simple, easy to understand and use, but based upon physically logical forms fitted to observed field data. So drought, as many of you I'm sure know, within the FWI system is estimated through the drought code. And the purpose of the drought code is to represent seasonal drought, such that when the DC is high, this signals an increase in the availability of deeper, denser fuels to burn. So the DC is weighted within the BUI such that when the DC is low, there's greater weight to the DMC, but then once things dry out more in these denser fuels, that there's greater weight to the DC, and so assumption is greater consumption. So the other purpose of the DC within the FWI system was it was developed to carry over drought from one season to the next through the overwinter adjustment. So just some drought code basics. So although the drought code wasn't necessarily developed to represent a particular layer, it has become associated with organic layers 15 to 18 centimeters deep that are deep and dense organic materials with a fuel load of 25 kilograms per meter squared. It has a maximum moisture content, gravimetric moisture content of 400% and a reservoir capacity of 100 millimeters. So because of this deep reservoir capacity and this denser fuels, it has a long time lag. And this long time lag of about 53 days is what allows the DC to overwinter from one season to the next. So although the DC does a pretty good job of identifying, times when you're getting greater consumption in these deeper organic materials and, which can lead to mop-up issues and deeper depths of burn, there are some questions that folks often have about the DC. And these questions include, what does the DC mean, especially in regions where we don't have these deep organic layers and we just have shallow duff, which is a lot of the areas of the boreal. And, so how can we measure the DC to try and to validate it? Other questions come up about overwintering. So should we overwinter or should we not? If so, how should we overwinter? When should we shut down the DC, and when should startup happen? And so I'm not going to deal with all of these questions in this talk. I'm trying to address some of them in my thesis, but what I'm going to try and focus on for this talk is are these objectives. So I've broken the talk up into two parts. The first part is looking at the DC validation. So showing the utility of electronic soil moisture probes to provide added intelligence about drought through the drought code. And the second part of the talk will focus on looking at the rationale of why we overwinter. So with the thought that, drought from the fall can carry over and affect spring fires. And then I want to try and provide some updated guidance on rules for DC startup, shutdown, and overwintering. I don't have all the answers, but I'm hoping to provide a little bit of information. And then to introduce a protocol we've been using in Ontario to measure the DC in the fall and again in the spring for DC startup. So the data that we're looking at for this talk is a combination of both field data, weather station data, and then we're also looking into new technologies like land surface modeling. So at each of these sites, the field data is soil moisture probes that we have installed, and I'll go into more details of the installation in the next few minutes, as well as soil temperature probes. We also, to calculate the FWI indices, including the DC, we have fire weather station data, as well as ECCC, Environment and Climate Change Canada weather station observations. And because we're interested in overwintering, we've also been collecting provincial snow observations. So we've also been looking at trying to see if land surface models that model soil moisture can be used to estimate things like drought code to correct the DC throughout the season. And I'm not going to go into a lot of detail about that in this talk, just the sake of time. But I just wanted to mention that we are looking at models, particularly this CALDIS, Canadian Land Data Assimilation System, which combines both remote sensing data with ground-based observations with high resolution numerical weather predictions. And so we also been using CALDIS for some of the snow data that we've been looking at. So I'm going to refer to it in the throughout the talk. So nothing, not a lot about CALDIS in this talk, but when I do refer to it, just so you guys know what I'm talking about. So so we've set up these moisture monitoring sites across the country. So we have one site at an aspen site at Red Earth Creek in Alberta, and a mixedwood site plot in Edson, another mixedwood plot in northwestern Ontario in Dryden, and then we have 4 plots, a jack pine, mixedwood, black spruce, and aspen plot in Chapleau. So, as you can see, not all these plots are your standard pine forest that the FWI system is based upon. We are exploring other fuel types, which is a common thing throughout the fuel moisture system. So just also pointing out at each of these plots that at each site, these are coincident with weather stations. So there's a fire weather station within 40 kilometers of each of these plots, soil moisture monitoring plots, and then we also have ECCC weather stations at each of these plots. And another thing I wanted to point out is that these field sites have been installed and maintained with collaborations with provincial agencies and other partners. So, throughout a lot of the development of the next generation tools and improvements, we're not, CFS isn't doing this on our own. We're trying to collaborate with others in order to make this happen and to make sure that things are useful to the folks that use the outputs. So part 1 of this DC validation. So just a couple things I wanted to point out for folks to keep in mind while I'm presenting the next couple slides. So these moisture probes are installed at angles from the surface. So the probes themselves, the tines are 20 centimeters long. And so we've installed them at 10 and 18 centimeters depths. And so depending upon the depth of the organic layer, these probes are installed at different angles. In order to achieve those depths, they go through the litter and through the organic layer, and then depending upon the depth of the organic material, they can be also installed into the interface with the mineral soil. So these moisture probes, they measure in volumetric moisture content. This is different. This is moisture based upon volume than what the drought code is looking at, and also the other moisture codes of the FWI system. They're measuring in gravimetric moisture content. So in order to go from volumetric to gravimetric, we need to know the bulk density. And since we don't want to disturb where all these probes are inserted, and so we don't know the exact bulk density of each of those sites, So it was easier to convert the DC to volumetric moisture content. And so we do that by taking the gravimetric moisture content of the DC and multiplying by the bulk density of the DC, which the standard is 139 kilograms per meter cubed. So this is important to keep in mind. So when I'm showing these graphs with volumetric moisture content, that just, some benchmarks, a DC value of 15. So that's, our starting DC values is approximately a volumetric moisture content of 54%, which is just under saturation on the gravimetric scale. A DC of 400 is closer to 20% volumetric moisture. So 400 pretty dry, 20%. 15 pretty wet DC, volumetric 54%. Okay, so just moving on here. So the first slides I wanted to show you is comparing the DC model with our observations of moisture at the depth of 18 centimeters. So here I've got our Chapleau mixedwood site. So of all those 7 moisture plots, this is our best, DC and observed moisture relationship. And then this Aspen site is the other bookend, is our worst relationship. And so for each of these slides, we've got volumetric moisture here on the y-axis, and then we've got date. And so we've got data from 2019, 2020, and 2021. And these, we've excluded the shoulder seasons, and we're just focusing on the late spring to late summer period. So May to into September. And so we've got a number of goodness of fit statistics here that are basically just showing the strength of fit, the error and the bias between the DC calculated from the nearest weather station to the observed moisture within these plots. So, as you can see, there's a bit of variability year to year, that depending upon the weather conditions, but overall, a pretty good relationship between the DC and these moisture probes installed at, in this case, it's 18 centimeters depth. And even this Aspen site, which kind of is our worst case example, still, you're getting a pretty good, what the wetting and drying events are being represented. It's just that there's a bias, and that the DC is assuming that things are wetter than what is actually being measured on the ground at that particular site. So, some variability between the different sites, and variability year to year. But another thing we found that we weren't necessarily, we shouldn't be surprised by, is that precipitation also made a difference. So we assume, based upon the FWI weather guides, that if your weather station, if you're within 40 kilometers of that weather station, that weather is representative of the conditions around that site. So, for this Dryden plot, we have AFFES, so we have a fire weather station at 39 kilometers, but we also had an ECCC station 7 kilometers away. So these top set of graphs, we have the weather calculated, the DC calculated based upon this further away station, and then these graphs on the bottom are with the closer weather station. And overall, what we found is that precipitation can make a difference. So if you're missing some precipitation events, that can mess up the DC calculation. So it's not that there's a problem with the DC, it's a problem with the inputs into the model. Another thing that we found was that overwintering can make a difference in the skill of the DC. So here we've got Red Earth Creek, data from Red Earth Creek for 2019 and 2020, and then we have Edson from 2019, 2020, and 2021. And so these top graphs, the DC is represented as it was calculated by the fire weather, by the agency the fire management agency, in Alberta. And then the bottom graphs, I recalculated the DC without overwintering. And so as you can see that, and we're looking at we're not, the very beginning of the season, but a little bit later into the season, that difference in by setting the DC much lower than it is actually, that can be maintained throughout a big portion of the season, especially in this 2019 example. And then again, in Edson in 2021, you can see that difference is carried out throughout the entire season, that the DC is actually predicting drier conditions than what is observed by the moisture probes at 18 centimeters depth. And so, we think that if we get if there is the DC is overwintered, is not done properly, that we think that, okay, well, as long as we get a big enough precipitation event, that's going to correct this. But what we need to remember is that the error, so the larger the error between what is actually the moisture on the ground and what is the DC is predicting it to be, the larger that error, the larger the precipitation event you need to correct the error. And so sometimes, some seasons, you don't get that large enough event to correct the error, and it can continue on throughout the season. So just a couple conclusions from this first part. I just wanted to reiterate that, we've been doing a lot of testing with these moisture probes. We've been inserting them at different depths and different forest types. And we have pretty good confidence that they can be used to relate to the moisture in the DC. I don't think it should be a surprise, but always good to point out that, if you want good moisture estimates from these moisture codes, you need good inputs. And precipitation is one of the inputs that can be quite variable. As well, errors in the DC due to overwintering can influence the whole season and result in bias throughout. So moving on next to the overwintering part. I just wanted to go over the basics of the overwintering adjustment. This adjustment was developed in the 1970s and essentially hasn't changed since. So the assumption is the adjustment is applied when the overwinter precipitation is less than 200 millimeters. So it is assumed that if you get more than 200 millimeters of precipitation over the winter period, that is sufficient to recharge any deficit that may have occurred from the previous fall. And so that 200 millimeters comes from the fact that the overwinter adjustment is based on moisture equivalence. With moisture equivalence, the moisture equivalent has a much larger reservoir capacity of 200 millimeters, which is the DC is currently based upon a moisture reservoir capacity of 100. So it's twice that. It is confusing, and there's confusion in the literature as well. And I got confused a few times, but it is something that needs to be pointed out. So basically, the spring moisture equivalent is equal to the carryover fraction of fall moisture. So if the DC is not measured up until the point that stations of freeze up or snow accumulation, that agencies can use this coefficient to estimate what the DC was in the fall. And then this is added to the overwinter precipitation multiplied by a constant by the wetting efficiency coefficient. So this wetting efficiency fraction is basically used to estimate how much of that overwinter precipitation actually becomes available for recharge. So basically, before I get into what comparisons that we made with what we actually saw on the ground with overwintering, I just wanted to point out this first study that we did that was basically looking at testing the rationale for should we overwinter or not. And so this is slightly different in that we use data in Alberta and Ontario again, though, but it was weather data and fire data from 1979 to 2018. And so we looked at, my mouse is being weird on me right now, and I can't get down to the bottom. Here we go. Okay, so basically we looked at in Alberta, Grand Prairie, Edson, Rocky Mountain House, and Lac La Biche. And in Ontario, we looked at Kenora, Dryden, Kirkland Lake, and Sudbury. And so, as we know, in the spring, the number of human-caused fires that occur each day is basically related to the FFMC. That we know the DC isn't having, or the DC of that season isn't having necessarily an influence at the time. But what we wanted to know is, if things were drier in the fall, does that carry over into the spring? So does it actually have an influence? Sorry. And so we wanted to compare. So if we add into this relationship between the number of human-caused fires and the FFMC, whether the DC was high or whether the DC was low, does that have an influence? And what we found was that yes, that you can get an increased number in a given day, an increased number of fires potentially occurring. So, one fire versus two fire isn't a lot within a given day, but when you add up the number of fires throughout the spring season, we did see that there was a significant % change in the number of fires that you could expect the following spring. So we saw increases between 20 to 260% for Rocky Mountain House in Alberta, 20% and 65% for Kirkland Lake in Ontario. So for the majority of sites, we did see an effect, an association with higher DC values in the fall related to increased number of fires the following spring. What we didn't see, we did the same with overwinter precipitation, and what we found was that the overwinter precipitation did not have as clear or consistent effect on spring fire activity. And that, so we didn't see what we'd expected, which was that if you have less overwinter precipitation, that you would potentially have more fires, and that wasn't a consistent finding. So then moving back to the overwintering and the field data that we had, that study basically gave us, reiterated that yes, that we, overwintering in some instances is important. And so maybe we need to relook at it to identify, where it's performing well and ways that we could potentially improve upon it. So the first thing we wanted to start with was the shutdown rules. So when do you calculate the DC in the fall, and what are the rules around that? So basically the rules as they currently stand is, there's 3 days where maximum temperature, air temperature is less than 5 degrees Celsius, the date of snow accumulation, the date of freeze up, or November 1st, whatever happens first. And then another rule that is often used is, agencies, once there's no more fires, then, turn off the weather stations. And then and that can often be months prior to freeze, these other conditions occurring. So then when that happens, then you have to estimate that carryover fraction, that A coefficient. So really we want to focus on these, some of these other attributes, so rules, sorry. So we removed the data freeze up because the sites that we're dealing with are predominantly snow, they're snow dominated regions. We didn't want to use November 1st because that seemed an arbitrary date. And we didn't want to use the, just end the season when there's no fires, because we know that, even though fires aren't occurring, there's still moisture exchange within the organic layers. So we wanted to test the implications of, if we used one of these 2 rules on the season, the shutdown of the DC. And in the spring, the current rules are 3 days where maximum temperature is greater than 12 degrees Celsius and 3 days post snow melt. And another thing we wanted to start to look at is what, when soils are actually thawed out. And I'll go into more details of that in just a minute. So starting with just the fall DC, the date when the DC shut down. So one thing, looking at all these different sites, these different plots for different years, we did observe that moisture changes pretty slowly in the fall. So here we've got, I have the volumetric moisture content on this axis. So I've got the black line is the 18 centimeter depth measured field moisture, and then the DC is the purple line converted to volumetric moisture. We've got soil temperature data is the orange line, and then on the top graph we have snow depth, which is the blue line, and then we've got precipitation events, which are the columns, which correspond to that axis. So one thing we found, in this instance for this year, the maximum air temperature threshold is met earlier. And that the snow accumulation threshold is met a little bit about a week or 2 later. And so, and these, often these 2 dates would occur quite close together, which is good because I think that the maximum air temperature rules were set up as a surrogate for when snow accumulation starts to occur. So in some instances they were, a day or 2 apart, and in some instances, like this instance, they were a couple weeks apart. But, I think what we're really trying to get at, especially since these, they're set up as surrogates, is when does that snow start to accumulate? And I think we have the data now to start to look, to be able to estimate when snow is starting to accumulate. So we have both observations, and then we also have remote sensing. So one thing that that CALDIS model, and, there are other models that through remote sensing and combined with observations are estimating snow. And so, but what we don't want to count is, this little snow event that happens in September. That isn't when, things are starting to shut down and the moisture is starting to slow down and the soils are starting to freeze up. It's when we actually start to get, this continuous accumulation. And even though we did get some melt periods after this, we found that that doesn't make a big difference in terms of the final moisture conditions in the fall. So in contrast, in the spring, we found, looking at these different sites and over, these different years, that it's more dynamic. There's more things going on. That complicates things a little bit. But basically, in this example here, that's set up very similarly, this maximum air temperature threshold is met first. We have snow melt, but this, now we're showing from March until May that melt happened quite early that particular year in early March. But the thing with these soil temperature probes now, we can see that these soils are still frozen. So we've got melt that's happened. We now have exposed soil. We now have exposed fine fuels, but they're sitting on top of frozen organic layers. And that can happen for potentially weeks up to a month, not months, but weeks afterwards. So, even though we're potentially starting the DC at this point when snow melts, that really, in future, should we maybe be looking at trying to start the DC when the soils start to thaw out? Because we really don't necessarily, we know that those deeper organic materials won't be involved in consumption anyway. So maybe we need to change that. Although I don't think we have the data to do it yet, but we may in the future. And so what I also wanted to point out, with some of this data that we have is that estimating that wetting efficiency, that B coefficient, isn't necessarily as simple as a single value, that there's a lot going on each year in terms of, how the timing of melt, the amount of runoff, the amount of sublimation, and whether soils are frozen or thawed. So, we've got 3 different years here of overwinter periods, and this is for the site that I have in Chapleau. So 2017 to 2018, 2019 to 2020, and 2020 to 2021. And so on the top graphs, I've got the snow depths, I've got precipitation, and then at that Chapleau site, I have multiple monitoring sites. So those are the black lines for the 4 sites that I have in different forest types. And then these orangey lines are the soil temperatures. And so I've added on here in the dotted line, that's the DC at 15. Volumetric content of about 54%. So, relatively saturated. So we've got, in this overwinter period, we have overwinter precipitation is, well over that 200 millimeters, but the fall volumetric moisture is about 48% on average between the 4 sites. And even though we've got a lot, we have a lot of moisture and we have a big snowpack, that volumetric moisture content isn't changing much the following spring. It's approximately the same. In contrast to the next year, we've still got a lot of overwinter precipitation, quite dry the previous fall. And then this spring, we do get a lot of recharge. There was a lot of snow and it's a late snow melt. And the melt is coincident with when the soils are thawed out. And so that may be coming into play and may be important to take into consideration. Versus this 2020-2021 overwinter period, we've got less overwinter precipitation, close, a little bit under that 200 millimeters, was quite dry again in the fall. And then, but in the spring, we're still, we aren't getting a lot of recharge. There wasn't as much snowpack, and there was an early melt. And so things melted when the soils are still frozen. And so that may, when that is happening, may also need to be taken into account, which is how do we do that with, picking between 0.5, 0.75, or 0.9 for this B coefficient. So a couple other observations that we made looking at these different data sets and observed data sets was that agencies that never overwinter the DC were sometimes introducing a false negative. So they were always assuming the DC starts at 15. So the DC, in some cases, there was a wet bias in the calculations. So it was typically wetter than what the conditions on the ground were. Versus there are instances where agencies that always overwinter and always use the same B coefficient introduce false positives, so dry bias. So the DC was often drier than what was actually being shown on the ground. So in fire danger, we want to reduce those false positives. So, where we have where we think that we have high fire danger, but in essence, we actually have low, and we want to eliminate those instances where we have false negatives. So where we think that the fire danger is low, but in actuality, it may be higher. So how can we do that in the short term, just based upon this model that we currently have? So I think we need to still, overwinter when the precipitation is 200 millimeters. And I think by actually measuring the DC in the fall up until the date of snow accumulation, we remove the need to estimate this carryover fraction of fall moisture. So that's one less coefficient that we have to estimate. And I think we have the data that we can do that. And then for now, I think we still, we estimate the overwinter precipitation from the date of snow accumulation until the date of snow melt. Eventually I think we can start, as I mentioned, start to look at things when the soils are thawed, but I don't think we have enough temperature data to do that. We don't have necessarily have the data to do that yet. And I think we need to vary the B coefficient, that wetting efficiency fraction, which is used to estimate how much moisture is from that snowpack is available for recharge. So, I was thinking, I was trying to calculate these. I was thinking about things like, if I was using a B of 0.9 at that Red Earth Creek site, it's a pretty boggy site. So I think that fits that description. A B value of 0.75 and, moderately drained sites. But I was also thinking about melt. So when melt happened later, more coincident with when those soils are thawing out, that you could assume that maybe there's more moisture available for recharge. And then using a B value of 0.5, in well-drained sites, that particularly when you have early conditions of early melt as well. So, thinking, if you're getting melt happening in early March and you are pretty good indication that things are, the organic layers below are still frozen, that it's less likely that that moisture is going to get into those organic layers. So just, some general thoughts I had while going through some of these examples. So in the long term, we want to try and update the overwinter. We want to update the overwinter adjustment model, but we want to maintain a simple model, but one that better represents the processes that affect spring moisture content. So we don't have all the answers. This is a limited data set. We only have, so much data, and we only have right now data for snow dominated areas. We don't have any data for snow free regions. And so but we are looking at exploring some different other variables so that we don't have to estimate this B coefficient based upon the overwinter precipitation. So I'm just showing some regression analyses looking at, what the actual spring volumetric moisture content is in relation to things like, from the CALDIS model, we've got snow water equivalent, what's the relationship to maximum air temperature, is there a relationship to snow depth, number of days between snow melt and soil thaw, or, from that CALDIS model as well, we can look at things like snow density. So I don't have any, silver bullets or ringers here, but just, to show that we are looking at, we need more data, and that we are looking at some other relationships to improve on the overwinter adjustment. So tying back to that first part that I had there, but if agencies are in a situation like Ontario was last year, Ontario saw DC values last summer above their 30-year maximums. So it was quite dry in Ontario at the end of the season last year. So Ontario wanted to know, based upon knowing that we were doing some work in this area, could they improve upon how they were measuring and overwintering the DC? And so we have these handheld moisture probes, which are very similar to the in situ probes that I was showing from the first part of the talk. And so we set up moisture sampling sites, these purple triangles, where we went and took actual handheld moisture measurements. And we did these at depths of 10 and 18 centimeters. And we did them within locations that were close to fire weather stations, as well as ECCC weather stations and snow monitoring sites. And then we also have the green squares, these sites at Dryden and Chapleau, where I have continuous monitoring. And so what this allowed us to do is assess, for these restricted fire zones, what, the regions, we were particularly just interested in the regions that we knew had elevated DC values. So we could then look at what was the DC from the weather station, what was it predicting, and what was the range of values that the DC are predicting. Now on this map, we just have the averages from the weather stations in those areas. And then at each of these these, I'm trying to get my mouse to work, but it doesn't want to get moved down. So, so these green balloons is where we did the moisture monitoring with the handheld moisture probes. And we also did some destructive sampling at those sites. And so what that was telling us is that for some of these regions, based upon the volumetric moisture content and relating it to the DC, that we could see that some of these regions were actually drier than what the DC was predicting. So we knew that moisture conditions were elevated, and maybe even elevated more so than what the DC was telling us. So then the plan is to go back out there this spring and remeasure these locations. And so that gives the province more information about, should they overwinter, and if so, how should they adjust their DC values? And it also gives us more data to try and improve, because we've also been, in these regions, we're also trying to monitor snow, and we're trying to look at some of those variables that I mentioned in that previous slide. Okay. So that was a lot, and hopefully that all made sense. But I just wanted to sort of end with sort of the take-home messages I'm hoping come from this. So these electronic moisture probes, I think, are quite useful to monitor and check the DC values the way that we've been using them. As well, I think that when DC values in the fall are quite high, that this can be an early indication of a need to overwinter. So I think that that's a good flag that folks should start to pay attention to what's happening in the overwinter period. As well, I think the overwinter precipitation isn't enough to tell us all that's happening. And I don't think that's the assumption of the overwinter adjustment anyways, but we need to pay more attention to how what's happening to that snow and how much of it is available for recharge. And again, like I said, we've only been looking at snow dominated areas, not areas that that don't receive a significant snowpack. As well, DC shutdown should occur at the time of snow accumulation, and this removes the need to estimate that A coefficient and the overwinter adjustment. So one last thing that needs to be estimated. Oops, sorry, I accidentally pressed that. As well, the FWI system startup should happen at snowmelt in the short term, but I think we need to maybe consider changing it so that we don't apply the adjustment until the soils have thawed, which may mean that we may need to hold the BUI constant until the soils have thawed out. We don't, as I said, we don't necessarily have the data to do that, but I think that's something we may need to consider, and maybe even keeping the DMC constant at that point. And although the overwintering adjustment isn't perfect, I think that following the rules that have been set up a little more closely can reduce some of the bias that we do see at some of the sites. And with that, I just want to say thank you everyone for listening, and also acknowledge some of the folks that have helped out with field work and getting some of the data necessary to conduct this project. And if there's any further questions that aren't addressed in the question period, that Mike and I can be contacted directly with our emails here. Thanks very much, everyone.
Well, thanks so much, Shailene, and Mike as well. Terrific presentation, really informative. I was thinking of some, different places that I've been, and various drought codes that came about, and some of the challenges that we've faced. And so I think this is really exciting stuff. There are a few questions already in the chat, so I'll move to that. And we have some time left too for questions. So folks, I'll just invite you to put questions in the chat, but I'll also ask you to come on and ask them. So the first question, Shailene, is from Andrew. Andrew, are you available to come on and ask your question?
Yeah, I was specifically curious about, you said in the fall and the spring about 3 days, specifically in the spring of above 12 degrees. I was just curious if they meant 3 consecutive days above 12 degrees,
Yes.
or just the after 3 general days.
No, sorry, it's 3 consecutive days.
That's what I thought. Thank you.
Thanks, Andrew. Marty, you have a question next. Are you on, Marty Alexander? Nope. I'll just read out his question. We'll see if you can answer it. So he asked, what should we consider as snow-free? For example, if a fire could make, say, a 1 kilometer run.
So I think there's two. I'm not sure if I'm getting what's coming to my mind is exactly what Marty's getting at, but what comes to my mind when he says that. So I think we need to consider snow-free in the open in terms of, fires that are, grass fires that we can occur, that where we still may have snow in the bush, and then there's snow-free in the forest. And I think that we currently are looking at snow-free just in the open because that's where our weather stations are, and you can get fires right after snow, we don't have snow, but that we also need to consider snow in the forest, which I think becomes more important and maybe more coincident with when we have that soil thawing, we start to care about those deeper organic materials when we have more forest fires from those grass fires. I hope that is addressing what Marty is getting at.
Okay, thank you, Shailene. Scott Murphy, are you able to come on and ask a question?
I am, and I was glad that Marty wasn't able to, because he's always a tough act to follow. So I was just reflecting on the fact that sometimes we use DC as a surrogate for fuel moisture in heavy fuels like logs and the larger branches and things like that. So I was just curious if that's something we're looking at as well. And then, yeah, the second part of that, if we refine DC so that it's doing a better job of tracking fuel moisture in the deep organics, do we kind of lose it as a tool or an indicator of moisture levels in our heavy fuels on the surface?
Yeah, we have been looking at that, and I do have and I didn't mention it, although we often, within the literature, there is, indication that it's, these deeper, denser organic materials or, coarse woody debris. And although that hasn't been validated, although in the States they have the 1,000R fuel, which is based upon these bigger, coarser, larger logs. And it's, similar time lag-ish to the DC. So I think we can make that association, but I do have a bunch of logs that have been sitting in the bush beside all my soil moisture probes, and we've been measuring them a couple times a year. It's just I haven't had a chance to integrate that into the thesis. So it is something that we are trying to look at, and that I think there may be a connection there. Does that answer your question, Scott?
Yeah, totally. Just curious. Thanks.
Thank you.
Okay, thanks, Shailene and Scott. Question from Juan Lee. Are you there, Juan Lee?
Okay, the question is just as I wrote there. Is there a way to model soil? So it seems that it is important for moving further.
Yeah, I think we could probably establish some models based upon the air temperature. I think those are probably out there, similar to the way that we've modeled or used the maximum air temperature as a surrogate to snow accumulation. But I think also models like CalDES that are remotely sensing attributes, and there's a big interest in terms of soil thaw for permafrost studies. And so I think that there are some products that we could potentially look at and try and validate that could give us some information. So I think we could either model or we could try and remotely sense, and there are folks interested in both.
Thanks.
Thank you, Juan Lee. There's one more question there from our colleagues. I think they're in Wood Buffalo National Park. Are you folks there to come on and ask that question? No. Okay, I'll just read it out. So I think they're asking about the trigger for spring startup. Was it 3 consecutive days of 12 degrees at noon or the daily high of 12 degrees? They say I thought it was at the noon reading.
There's a subtle difference, and maybe Watton can talk to this more so because he's behind the maximum, and Flanagan behind the maximum 12-degree noon, because I think earlier on, I think it's in the FWI fire weather index guide from Turner and Lawson that it's the noon value, and then from Watton and Flanagan from 1993, it's adjusted to the maximum value, 12 degrees. I'm not sure why the subtle difference, but Mike, I don't know if you could speak to that.
I could a bit, yeah, or for a long time, but no, ultimately, these temperature criteria are just surrogates to use to try to make an estimate of when the snow's gone in the bush, and really it should be when the ground is thawed as well, when those calculations, right? I mean, you made that point. So when we did, I think we switched to 12 degrees max when we did a bunch of analysis with some snow data and saw that it was disappearing, earlier in time. And so this was just a, historical analysis, and it did, it seemed to indicate that the snow was gone in the bush. If that was the criteria that we were going to use, it was gone a bit earlier. So yeah, it is a bit of a difference. Probably, I mean, for consistency, if one, goes back to the weather guide, yeah, it is that noon observation because that's what's being recorded. And this, I'm hoping that we will put out some, we'll have a look at some of these criteria and reevaluate them with some data. Now that we are, making some revisions to the FWI system, anyways, that we will put out some new guidance that is more tied to, obviously, if the ground is frozen, but but there's no snow cover, then that that litter fuel that's there, be it, a nice exposed grassland or a litter layer. I'm answering the next question too, I think, even though I didn't quite read it. Like that will carry a fire. And so, I mean, that's what's important. It's like we should be calculating at least the FMC. And you talked, I think, a little bit about the spring station idea that some agencies use, Shalene. So I think it's important to think about, when are we starting the calculations, and just to have again, it may lead to some differences, some inconsistencies with a simple weather-based criteria, but I think in terms of the actual calculations and moisture exchange, bookkeeping system side of it, it will turn out better. But honestly, I didn't read that last question as it popped up there. I just saw this, so I just decided to ramble on further.
I think you hit it right. It was Mike Flanagan asking, can we have a fire with frozen ground, and probably meaning how relevant is that? And so I think you addressed that nicely. And we're really getting to the end of our time. So I just wanted to make sure there's time enough to say thanks very much to Shailene and Mike. Really appreciate the presentation. Thanks for being part of our National Conversation series, and be terrific to see you back again in the future for updates. Sounds like there's lots of interesting stuff happening here. And thanks for everyone for joining us today too. I appreciate the attendance as well. All right, take care, folks. Have a lovely afternoon.
Thank you. Take care, everyone.
Thanks, everyone.